Hello, I'm Jeffrey Fox, the instructor for Big Data, Open Source Software and Projects. We're going to the Part C of the application structures discussion. And if you remember, we introduced a page of features, a slide of features, and we were going through describing what we meant by the features. And a critical feature was streaming. And in fact, 80% of the applications we suggested exhibited streaming characteristics. So this is a very important feature of big data, and we'd like to discuss that a little. So this is a picture we referenced before, and it's one I've used many times. I built it a long time ago, and it basically points out that the world consists of sources of data, which are these things arranged around the edge. And those sources of data, which vary from seismic arrays here, water measures here, gene sequences here, satellites, other systems, namely here's another grid, computers on the Hadoop cluster, storage systems, databases, Large Hadron Colliders, clouds. They sort of data on his smartphones from people. They pour data into an ecosystem, which ecosystem consists of services. That's what the S lying around here is, essentially services. And those services go through processing, filters. And they go through processes to try to work out, fuse data together to see what they all imply and things like that. And then it all ends up somewhere where people look at it and make decisions. So, and this then exhibits this well-known pipeline. Raw data becomes information, becomes knowledge, becomes wisdom, becomes decisions. I sometimes call this a DIKW, data, information, knowledge, wisdom pipeline. So this actually over here labels these things SS, a sensor exchanges or services. It just says that the smartphone is made to look like a service. And of course, all of this involves workflow and orchestration to take all these sources of data and assemble them into what we want. So this I put this slide here because it really is all streaming. This is what these arrows mean. The data is streaming around from service to service, from instrument to service. And that's sort of the nature of today's big data world. So here we come to the streaming category. You may remember that that was a very important category, which was over 80% of the applications were involved in. And we will see some real, actually go through some examples. We've even seen some of it already. But if we look at what's involved in streaming, there are the devices themselves, such as the parts of a smartphone, robots, and what have you, the Internet of Things. And then there's just people. People produce streaming because those streaming is just a time series. And somebody typing away is producing a time series of information which it looks architecturally pretty similar to a smartphone burbling away. In fact, the person might be actually talking into the smartphone or typing into the smartphone. So people and things and devices actually look pretty similar as far as streaming is concerned. And the popularity of Twitter and Facebook and Snapchat and things and everything has led to effectively a lot of streaming type data. When we come to technology, we will see Apache Storm. There also is S4 and Samza from Apache addressing streaming data. This type of data is critical because it has some methodologies and architectures allowing it to gather and integrate these multiple erratic streams. There are lots of them because there are lots of people and devices, and they're erratic because sometimes the people are asleep, sometimes they're banging away fast, and so on. So they're completely asynchronous, erratic. However, each of them is independent and each of them is relatively small. None of these devices in the Internet of Things or people are producing lots of data. The sum over all people is lots, but not any one person. So that means that in the cloud, they can be supported by multiple cores, each core doing one thing or a few things or a few people. There's also lots of interesting algorithms because as your data comes in, you're not going to rerun your clustering. You've added 10 points to your set of 1,000,000 points. You don't really want to rerun the clustering to do 1,000,010 points. You actually want to just update the clustering for those 10 points and so on. And so you need to have new algorithms which are incremental, and they cope with data changing in small amounts, or possibly even large amounts in total, but they're changing in time, so in a small interval of time, they just change by a little. You can actually imagine doing this in a sort of hybrid fashion. Every now and then you run the classic batch algorithm on how much ever data you have at the moment. But then as the data comes in, you increment the results of that batch algorithm with the streaming data. And when you get enough streaming data, namely say another 10% of the data becomes in and streamed, then you rerun the batch algorithm. Here is an example from the smartphone area where we look at the MEMS devices, the electronic devices inside smartphones and related devices, laptops, headsets, tablets. Smartphone is the largest, and you can see we have 8 billion such things in 2013. And so this points out that sensors are very important, devices are very important. They always stream when they upload their data, and they happen to be dominated by smartphones, which is generally true. When you look at sensor work in say academia, a lot of the interesting work is built around smartphones because they're the most pervasively available sensors. Next, we have another example in the following slide, which covers those devices which live in the home. If you look at this, you can see that we have a 60% compound average growth for over the next 5 years. It's going up from 100 million now to 600 million. So these are your webcams, smoke sensors, power monitors, everything, your baby monitors, everything you want to monitor in the home. The connected home has been predicted for a long time. I remember I bought a bunch of books in it in the late 90s. I never did anything because it didn't seem to be quite there, and it's still really not quite there. But this graph here claims it's going to explode. So let's hope that's true. Although it really matters, but I expect it's going to be true. Things have changed. Thank you. So an important thing about these streaming data is typically each thing that's streamed is pretty small, and they're well suited to clouds because every streamed information can come and land on a single core running on a virtual machine. And so it has this pleasingly parallel feature that every streamed piece of data can be processed independently. Well, so the cloud is basically placed in integrated fashion. It controls the things that are streaming. Namely, if you're sitting there at the cloud, you're getting controlled by it because it's telling you what to do. It can also do intelligent searches, like if you want to find out where the nearest hotel is or the nearest recreation place, you can find that from the cloud by looking at your smartphone. If you're a robot, the cloud can look at your images and decide give you some strategic information about what to do. So this is called, here the cloud operates what we call sensors as a service, where each sensor, here we have a Connect, here a smartphone, here a Lego robot, is sort of processed. Here's some data coming in from the North Pole on radar sensors, so seismic sensors. Actually you have sort of output sensors here, which are the stream results of the computation. Here it's a stream result of a snow, ice, and air snow interface. And as I pointed out many times, there are meant to be somewhere between 24 and 50 billion devices in the Internet of Things by the year 2020. Now we come on, so that was the end of our discussion of streaming, which was the end category in our first set of features. Now we have a new set of features which we'll discuss. And first is sort of the classic database category. You do a search, a query, and an index. 12 of the 51 were in that category. These, of course, can, in the modern world, if you want to, use MapReduce or MapReduce enhanced database like Hive or Drill or something like that, if you want to, or else you can use classic databases. A very important category is the category that categorizes, namely, or classifies, namely. This says that 30 out of the 51 problems involving dividing data into categories. That uses machine learning with lots of different methods, from support vector machines, clustering, learning networks, Bayesian methods, random forests, and so on. Especially important area in e-commerce is collaborative filtering, because that drives recommender engines, which is a key commercial application, tends to use MapReduce, and the typical algorithm is the algorithm that finds your nearest neighbors. Now, we will dwell on this a bit, but machine learning is what you might call the cosmic classification of algorithms. I should, by the way, stress that these features are not independent, namely an application that does classification almost certainly uses machine learning. So these sort of overlap. So if we look at machine learning, we have two important types. Local machine learning. Here we have an example, is a bunch of images. Those images running on independent cores of our virtual machine. And each of those images has maybe a machine learning algorithm applied to it to classify it. So this is running pleasingly parallel implementations of R or something like that, or ImageJ, the image processing library. Now that's differentiated, this is the most common, 36, but there is also global machine learning. That's where you do not run each piece of data independently, but rather all the data, or some large, some data, lots of the data, including data in lots of different nodes of your parallel machine, are involved in some machine learning algorithm. That's true when you do deep learning, clustering, latent dirichlet allocation, etc., multidimensional scaling. These are all large-scale optimizations, and we will have a little slide on discussing this. You see terms like variational Bayes, MCMC, lifted belief propagation, stochastic gradient descent. Here's another way of processing. LBFGS is another way of processing Newton's method, Levenberg-McQuart, and so on. I sometimes call this exascale global optimization, or EGO. So now let's come and go into details of each of this feature. This part does not have all these details. It starts with some words on the sort of what you might call the most classic of these features, the search query index category, which is the classic database problem. Here, of course, what's notable is that we've learned how to make very good indices for quick query response. Also, current databases from Oracle and others are done extremely well. The cloud has emphasized alternative solutions based on Hadoop and NoSQL databases like HBase. And one thing you can, if you won't think, is that actually these are the same approach. The only difference is that they're focusing on different aspects of the same solution. MapReduce phase is focusing on how to get parallel implementation, whereas your Oracle database or MySQL database is focusing on very, very fault-tolerant, robust results without necessarily getting the highest performance or the most cost-effective solution. We note that the NoSQL solutions have somewhat different data abstractions. Databases have a very strict schema on write. You have the schemas all fixed when you write your data, so it's all the schemas are not very flexible, whereas NoSQL systems support very different data abstractions. Tables with tables are still very popular, as what you get in databases, but the schemas are often more flexible. But not only you get tables, you get objects. We stressed before we get graphs, and of course you just get documents. Then there are tools like Drill, which make everything look like SQL. And Hive on HBase, some sense does that. Here is another of the categories we introduced: classify and collaborative filtering. So everything, lots of things involve classification. In fact, you can say search is classifying documents by the nearest to your search term. Recommender engines are classifying items by the relevance to their interest. And if you do, say, network science studies, you're dividing people in the internet into communities of like-minded folks. Biologists classify sequences by their role in the family, species, genre, and things like that, to what they genus, to what they belong. Classification is almost by definition implemented by machine learning. Support vector machines chops the data up by planes. Clustering divides the data into groups, where the member of each group are near each other. Clustering is unsupervised learning, as there's no input into where the clusters are. Some clustering algorithms require you to input the number of clusters, but not all. I say collaborative filtering is supervised, as it uses existing rankings to predict new rankings. And it's a very well-known approach for recommender systems that matches the current user's interests with those of others to predict interesting data for the user to look at. And there are actually three types of collaborative filtering: user-based, item-based, and content-based. And they can be combined in hybrid fashions. Learning networks are another approach. They train using typically existing classifications, such if you have a bunch of images, you label those images, you learn those labels. That's the learning phase of the learning network. And then the learning network takes new images and classifies them according to what is learned from previous images. Sometimes, actually, learning networks can either be supervised or unsupervised. This use case 26 of deep learning has both categories. So now we come to the second set of features that will be in the next part, which will include machine learning. Thank you.